All right, here are solutions to perfect problem 4 for Math 243. So we're given this stem and leaf plot, which showed up earlier in this class. It shows the height of 90 mountains. The smallest is 0.5 kilometers. The largest is 19 kilometers. It tells me here that the average height is 5.31 kilometers. The standard deviation is 4.12. And the distribution appears to be right skewed. Yeah, that looks right. If you turn this to the side, it looks like it has a tail out to the right and most of the data to the left. So what it's saying is use the table of random numbers in the back of your book, which I copied right here. This is row 8, row 9, and row 10, to choose 12 groups of 3 mountains. And then it kind of gives some information on that. And then what we want to do is calculate the average height of each of the 12 groups, and then calculate the average and standard deviation of these averages. So, okay, a lot of work to do. I'll do the first few to show you how to do these. So group 1. We want to find 3 mountains. The first one we'll get by finding the 46th mountain. So I numbered these here. Let's see, 40, 1, 2, 3, 4, 5, 6. So the 46th mountain is 3.8 kilometers. And then the next one would be the 82nd mountain. The 82nd mountain, here's 80, so 81, 82 would be 11.5. And then the next one is the 72nd mountain. 71, 2 is 79, 7.9. And then we do group 2. Group 2, the first mountain should be the 59th one. So here's 60, here's 59, 4.5. And the next one is the 6th mountain, 06. So 1, 2, 3, 4, 5, 6 is 0.9. And the next one is the 64th mountain. 60, 1, 2, 3, 4, 5.7. So I think that's about enough. You continue doing this, you're going to make 12 groups. So I'm going to go ahead and pause the video and do that because you don't have to watch me do all that, but you can kind of follow in this fashion. Okay, so what I've done here is I pulled in the data for all 12 groups, kind of following these random numbers up here. And then I also averaged each of the groups. So what I ended up with is 12 averages listed here in black. And then all the numbers here are color coordinated, and I underlined them in that color to show you where they came from. So hopefully that's all clear. So I generated a ton of data. I know this is kind of tedious, but I'm not just doing it to waste your time. I think there's a little bit of a payoff here. Going back up to the instructions here. So we've now taken care of this group. Now it's saying calculate the average height of each of your 12 groups. Okay, did that. Then calculate the average and standard deviation of these averages. And then comment on these values, comparing them to what you expected. Okay, so what that's saying is take these 12 data points that we have here, all these averages, and add all of those up. So this is kind of saying the average of the x bars and the standard deviation, standard deviation of the x bars. So now my data is not these guys in color, but it's just these averages down here. That is the data I'm going to look at. So I'm going to put each of those 12 data points into a calculator and figure out what their average is and figure out what their standard deviation is. Put all these into a list. I did one variable statistics on it, and what I got is the average of these 12 data points is 5.215. Maybe I'll just call it 5.2. Okay, and the standard deviation was 2.50. Call it 2.5. And what it wants me to do is compare these to what I expected these values to be. Okay, so what I I'll write down here, expected values of these. I can put right next to them here. The expected average of the x bars is just the same as the average of all of my data points. So up here it tells me the average height is 5.31. So I would have expected this to be 5.31. Ended up being 5.2, pretty damn close there. The standard deviation, what I expected this to be, is my standard deviation of the whole group was 4.12 up here. But the number of observations in each group is 3. So I expected this thing right here to be 4.12 divided by the square root of 3. And if you plug in 4.12 divided by the square root of 3 in a calculator, what you get is 2.378. So I expected the standard deviation to be 2.4. They ended up being 2.5. So both of these values, actual values, were very similar. To expected values. Okay, and the last thing it wants me to do is comment on the shape of the distribution of these 12 averages right here. There's a few different ways to do that. I think what I'm going to do is I'm going to make a histogram. And for my histogram here, I'm going to group these kind of, this first group is everything from 0 to 2. And this is if you're bigger than 2 but less than 4. So maybe 2.1 to 4. And this is 4.1 to 6. And this is 6.1 to 8. And this is 8.1 to 10. And is that enough? Nope, I need one more. This out here is 10.1 to 12. Okay, these values down here are a little misleading because really this isn't 4.1 to 6, it's 4.000001 to 6. My point is 4.0 would go in this one. Anything bigger than 4.0 would go in this one over here. So, okay, let's see. How many do I have in the 0 to 2 range? Looks like just this one right here. So we'll make this height 1. How many do I have in the 2 to 4 range? So I've already taken care of this guy. 2 to 4, 1, 2, 3, 4, 5. 5 of them in the 2 to 4 range. So I'll need this guy to be quite a bit taller. This up here is 5. 4.1 to 6. Let's see, we got 1, 2. Looks like that's it. So 2. Do something like this. 6.1 to 8. 1, 2. 8 to 10. Looks like we got 1. And 10 and above, 10 to 12, we got 1. So here's the shape of our distribution. It still looks like it's right skewed. The reason this still looks like it's right skewed is two things. Our value of n wasn't too high, it was only 3. If we had made n higher, this would start to look more normal. And our data started out very right skewed. But the point I want to make is maybe this is still right skewed. This still appears right skewed. But maybe less so than our original distribution. This was very right skewed. I mean, this guy was way out here compared to these. This one's still right skewed, but it's not as bad. It's starting to kind of take on this bell-shaped distribution. We're not quite there yet, but we're heading in the right direction. So this still appears right skewed, but not by as much as original data. Of course, our central limit theorem tells us that as n gets large enough, this thing will start to look just like a normal distribution. Our book has us use 30 as the cutoff for n, so we only use 3 here. It would have been nice to use n as 5 or 10 or something so that this really did start to look normal, but this was a lot of work for you guys just to get this data like this, so I didn't want to make you calculate too many numbers. So hopefully what I want you to get out of this is, okay, I'm starting to see the central limit theorem work in here. This distribution's starting to look normal even though it's not quite there yet. Our average of these averages is about the same as the average of all the data points. And the standard deviation of these averages is about what we would expect, the standard deviation of all the points divided by the square root of n. So that is the end of this kind of tedious perfect problem.